Let me begin my presentation.
So here are the contents of my presentation. First of all, I give you a bit of background of our research. Then I will brief all of you about unsaturated soil mechanics, which are highly relevant to my presentation today. Then I will tell you what are our theoretical consideration of a new 3-layer all-weather cover system without using geomembrane, but vegetation. Then I will report to you our 1D and 2D tests using recycled concrete with different plant species. Then I'll move on to report to you our field monitoring results over 6 years of the new 3-layer final cover system using recycled concrete with and without vegetation. Finally, I will draw conclusions and deliverables. So here's a chart showing the composition of waste in Hong Kong. Then what you can see here, actually the construction waste counted towards at least 25% of the total waste generated each year in Hong Kong. How about in mainland China? And actually, probably you know better than me, actually the waste increase, solid waste increase about 10% per year. And actually 40% of them are out of the total waste are construction waste. Here are the statistics from North America, Then what you can see here, actually the construction waste counts towards 2/3 of the total waste. So obviously construction waste are big problems, and also construction waste cannot be incinerated. That means cannot be burned, okay, economically and effectively. So we have to find a way how to deal with them. So a traditional way is by landfilling of solid waste, including construction waste. And there are some basic requirements of final cover, which is to prevent water infiltration, minimize gas emission, and also have to be environmentally friendly. So on the left-hand side is a typical final cover system design, and which use geomembrane together with compacted clay layer to prevent infiltration and minimize gas emission. But what you can see the photograph on the right-hand side, there's can create actually interface failures has been widely reported over the years. And also the geomembrane are vulnerable to defects and holes and created during construction. And also they may have durability problem, and also the clay underneath can desiccate, create cracks, induce problems as well. So in other words, there could be high maintenance costs. So an alternative solution should be considered. Now, those are the couple of pictures taken from a sorting plant in Shenzhen. So what you can see here is the construction waste are being broken down into different particle sizes in the plants, and they can produce particle sizes from the recycled concrete ranging from 30 to 40 mm, which is a graphite size, and down to 1 to 3 mm fine sand. And actually they are selling in some ways relatively low cost. Okay, 20 hours. So scientific engineering for us is, or at least for my research group at that time, is we ask ourselves, can we make use of the construction waste to reduce CO2 emissions directly or indirectly, and also to improve the robustness of the final landfill cover. Now let me move on to a brief introduction of unsaturated soil mechanics. Saturated soil, as we hope we all know, that is a special case of unsaturated soil, i.e. when the degree of saturation is 100%. And landfill cover is unsaturated. Okay, no one will build a landfill below water table. And actually, rainwater is very hard to saturate the cover. Let me check the see whether any problem now. Okay, now everybody can hear. Good. Okay. Oh. Now, if I tell you clay is more permeable to water than gravel, you must think I'm crazy, right? That's what you have learned when you were undergraduate student, right? But I'm telling you, this is true, okay? When the soil is unsaturated. Now let's look at the Darcy's law on the left-hand side. V equal to minus KWI. KW in your undergraduate course, your professors will typically tell you, which is almost a constant because it's a function of void ratio. And the degree of saturation is 100% because soil is saturated. So in other words, if we move on to the left-hand side figure, then you can see clay is less permeable than gravel when the soil is saturated or almost saturated. But if you move along, when the suction is increased, say beyond an arbitrary number, let's say S1, that may be 10 kPa or maybe 5 kPa, then what you can see, actually the permeability of gravelly sand, for example, decrease rapidly, but the clay remain almost flat until the suction getting fairly high. So when the degree of saturation decrease, hence suction increase, then the permeability of gravel is lower than clay. And those have been proven by many experiments. To explain that, one may use just a simple diagram to illustrate. If you look at on the left-hand side, low suction means high water content. Water can find the black line, water can find its way down easily through those blue shaded areas that represent water. When the water content decrease in a partially saturated soil, then the flow of water will find a long path to tortuous long path, okay, shown by the red dotted line here. That means the permeability decrease. Now on the extreme, on the right-hand side, actually the water cannot get through because of low water content. The white shaded area is air. Now remember, air is not conducting to water, same as air is not conducting to heat. Okay, so for water to get through air, can only go through diffusion, and which is a long process. That's why when you have many voids in the soil, actually the permeability decrease. And gravel obviously have more voids than sand, than sand. Then that's why gravel has less permeability when it's unsaturated. Now, since our landfill cover also involve vegetation, so let me just also briefly introduce a bit of botany, if you like. Now, I'm sure you still remember when you were in the school days and your teacher have told you photosynthesis. So when plants to produce glycose require water from the roots. So that's why I showed this equation here on the top left-hand side. And when the water is being sucked out from the soil, actually creates matrix suction, which is shown by this equation here. I purposely color those terms related to plants in green. So by increasing suction in the soil, actually we increase shear strength. But just the opposite, when the suction increase, that means the moisture content decrease, actually permeability also decrease. Now that's the beauty of that. So let me do a recap. When suction increase shear strength, but reduce permeability, and which is good sign for our landfill cover. Okay. Now, if you're interested in what I just said, and of course, please take a look of my textbook, 2007 Advanced Unsaturated Soil Mechanics Engineering. And also, if you're interested in plants, then a recent book is Plant Soil Slope Interaction. They both are published by CRC Press. So let me report to you what are our theoretical considerations about this three layers system without using geomembrane. So we borrowed the concept developed in US in the 90s, so-called capillary barrier effect, CCBE. And what was the idea in those days, in the 90s? using, if you move on to the left-hand side diagram, okay. I don't know whether, let me see whether I can use my pointer. Let me find out. There's a bit of problem. Okay, then forget it. Okay, if you look at the figure on the left-hand side, then what you see when the soil is unsaturated, then coarse material has lower permeability than the fine-grained material. For example, gravel is less permeable than sand. Then what people can do at that time was to use this effect. So that means water getting in, and in the fine sand, fine-grained soil, and then will be supported or stopped by the coarse-grained material underneath, means gravel. And only when the suction decrease to a certain extent, or water content increase to a certain extent, then water will start to break through this the second layer. That's what we call water can break through under humid condition. So that's why geomembrane is still needed. And this type of design is good for arid and semi-arid regions, meaning the any rainfall less than say 800 mm per year, but it's not relevant or it's not appropriate for humid region, which is any rainfall more than 800 mm per year. So our idea, or our new idea, is to introduce one additional layer at the bottom of the capillary barrier system, shown by the middle figure of the slide. By introduce the low permeability soil, which is shown in red here, then that means when the water break through the coarse grain soil, infiltrated water can be stopped by low permeability soil, for example, clay, for instance. So in other words, it becomes an all weather. So whether it's a humid weather or it's a dry weather, this three-layer cover system can take care of all conditions. Hence, no geomembrane is required. Now, how about gas emission? And we investigate this both experimentally and also numerically. And actually, when we put in the low permeability gas, fine-grained soil at the bottom, for example, a silty material, and then we carry out laboratory testing and numerical simulation, what we find are some typical results shown on the right-hand side here. But in the interest of time today, I will not go into detail on this. And if you're interested, please go to look for our paper published in Waste Management and also Riddlestone Journal. Okay, both papers describe this type of experiments and numerical simulation in detail. Now, again, this is without geomembrane. So let me focus on today's presentation here. So our objective is to investigate, okay, or explore the vegetated three-layer landfill cover system with recycled concrete. So we carry out field monitoring and also physical model tests, including 1D soil column and 2D in a 3-meter long flume, and plus theoretical and numerical simulations. And today I will only concentrate on the physical modeling and also field monitoring. So here are our particle size distribution we use in our experiments. Today, of course, I can only report to you a small fraction of our experimental results. And I would like to draw your attention on the right-hand side photograph. On the top there is FRC, fine recycled concrete. And the middle there is a coarse recycled concrete. And the bottom is completely decomposed volcanic soil, which is a clay silt naturally available in the southern part of China, including Hong Kong. And here is one typical setup of our 1D water infiltration test. Consists of a topsoil, which is used for plants to grow, and which is made of non-engineering soil called CDG, complete decomposed granite, and then followed by FRC, CRC, and then CTV. And along this soil column, actually we have 8 transducer tensiometers to measure suction, and also 8 volumetric water content sensor to measure the distribution of water content. So here's a picture showing 3 experiments were carried out at the same time. On the left is a bare column, and that means no plants at all. And then in the middle is a middle column planted with shrubs. Okay, and then on the right is a planted with grass. And those 3 soil columns were subject to evaporation and then ponding. The ponding experiment is obviously very important. Probably the most important for our research here is to simulate about 1,000 year return period of rainfall. Okay, we ponded 48 hours. Now please remember, no geomembrane, okay, was used in any of the soil column. So let me show you some results here. What you are seeing here is a plot of matrix suction versus depth of the soil column. And in the middle part here, the black line shows the initial suction in the bare column. And the red one is the grass, and then the blue solid line is the column vegetated with shrubs. Okay, so what you are seeing here, the shrubs create much higher suction than grass and then bare slope, because of photosynthesis, right? We require water has to suck in to the plants. In other words, to the leaves to create photosynthesis. So this is, I would say, expected. Now, how about ponding? After 48 hours ponding, as I said earlier on, is equivalent to 1,000 year return period. Then what we are looking at, perhaps let me draw the attention to this the result in the circle here. Okay, in the bare column, the suction is almost destroyed or disappeared. Okay, down to CRC layer, and still have a bit of suction retain above, say, 5 kPa or so in the column with grass, but fairly high suction still retain is in the order above 18 or so, actually in close to 20 in the soil column planted with shrubs. Okay, so in other words, there's no water go through the bottom of CDV. Okay, and if we concentrate this time to the suction measured in the CDV layer, then what you can see here, okay, the suction actually remain almost unchanged after ponding in CDV layer in the 2 vegetated soil column. So what does that mean? Means actually no water got through CDV layer, okay, in the vegetated soil layer, vegetated soil column. There's a water getting into the bare column. Okay, that's why the suction reduced from the original initially in the order of 20 or so now to less than 10. Now let's move on to the 2D full model tests. Now we actually construct this similar layer in this 2D soil flow model, which is 3 meters long. What you can see here in the picture, top layer is FRC, CRC, and CDV. Okay, and on top of this flume, we have a rainfall system and installed to impose different raining conditions on this 3-layer cover system.
Okay, you have 5 minutes.
Okay. Now there's no geomembrane use. Okay, and the flume is heavily instrumented. And let me just show you some results here. Now, after 100 year return period and along the 3 sessions ABC, what you can see, the measured suction distribution are fairly consistent along the 3 sessions. So I will just draw the most critical section to discuss today here is section CC. Okay, so what you are seeing is section CC in the CDV layer. There's no change of measure suction after 100-year return period. So in other words, no water can get through. And consistent with also from the volumetric water content measurements, okay, again, along the 3 sessions, okay, and if you concentrate section CC, which is the most critical one, and again, you can see the water content measurement consistent with major suction measurements, there are no indication of any water will get through. And of course, physically, we did not measure any water going through the 3-layer system. Okay, I'll skip that. Let's go to the field. Okay, so this is our field test site in Xiaping, and one of the largest landfill site in the Canton province. So our test site is 12 meters by 20 meters on site there. On the left-hand side is a bare construction. On the right-hand side, it is a cover with Bermuda grass. So rainfall there is over 20 mm per year. And for this field monitoring, there's no geomembrane use as I described before. So we put a lot of instruments on site, but I would like to draw your attention to the result from 6 lysimeters, measure water, any water flow through the 3-layer cover system. So this is a cross section of the instrumentation. Again, I will not go into detail. I just show you the result, okay, from this lysimeter. So here's a measurement of over 6 years, okay, starting from 2016 to now June 2022. And what you can see here on the green one is the cumulative rainfall over the 6 years, over 12,000. So on average, is over 2,000 mm per year. Okay, it's a very humid region. And what you see from the measurement, cumulative percolation from the 6 lysimeters. The blue lines represent from the measurement on the bare cover. The red lines represent from the vegetative cover by grass. So the maximum measured percolation over the 6 years is 124 mm. So divided by 6, okay, is only 21. And for the grass, for the bare cover, for the grass one is less than that, is 19. Okay, so in other words, grass reduce another 10% of percolation, and this type of 21 or 19 is way below 30 mm per year by U.S. the Department of Environment. So grass cover actually reduce percolation by up to 10%, which is very helpful. How about gas emission? We also install the gas meter, and what we measure is a tiny increase of gas pressure. Okay. Now, recently also recently means about 2 years ago, we also carry out effects of biocharts on recycled concrete. So again, similarly, I would like to draw your attention. For this layer, we have here's a cross section on the right. So FRC 5% biochar and the GRC, and then the bottom is FRC plus 10% of bentonite. So let me show you again, no geomembrane. Let me show you the results. Okay. And the cumulative rainfall and is very high, as you can see from the figure, but the important one is the cumulative percolation. Okay. Again, it's very small. And then if you combine the 2 sets of results we obtain, one from the over the 6 year, one over the 1.5 years, 2 monitoring sites, then we can draw the conclusion here. They are all the measurements well below 30 mm per year. So this is the one with biocharts. Again, remind everybody, no geomembrane. Okay, conclusions. Okay, I hope I convince you in our lab, using recycled concrete with sufficient permeability of the soil property actually can be a substitute for the 3-layer cover system based on 6-year monitoring and below 30 mm per year. And then the grass landfill cover system actually enhance the effectiveness by about 10%. And the 3-layer system can effectively minimize gas emission. And also, recent study, we also study biochar effect, and use of biochar also is a very promising approach. And since we don't use geomembrane, that means the capacity of landfill can be increased by using a steeper slope angle. for landfill site. That means enhance the capacity of a landfill. So deliverables, okay, prevent water infiltration, minimize gas emission, environmentally friendly use recycled concrete, okay, and actually can be cost-free, right? And then self-regenerate and sustainable approach using natural plants. Capacity can be increased of landfill sites. Remember, no geomembrane. So all the material from the cover are recycled concrete or natural material. And actually, the approach now is being adopted in the draft code of Chinese National Code of Practice. And here's a list of publications if you're interested in geotechnique, recent one, 2022, and Canadian and Zhejiang universities, and those science of total environment, etc. I hope you are interested to take a look. Thank you for your attention.